Welcome students. Today we are studying about occurrence of superconductivity and persistent current. In the previous lecture we have discussed what is superconductors, what are superconductors and how this has very significance for us. In this lecture of condensed matter physics part 2 unit 5, we will learn about various type of superconductivity with reference to transition temperature and the idea of persistent current. The current that may have many applications for us. A current which is without any external source. How it can be developed and what are the applications we will discuss in this lecture. Following is the outlines of our lecture. With the learning outcome and student effective learning outcome, we will move to superconductors, superconductivity, something that is discovered by Kamerlingh Onnes in 1911. Then the biggest challenge that was associated with the superconductors was about temperature, transition temperature. So most of them tried to increase the temperature. So we have discussed here occurrence of superconductors, superconductivity in many elements, then compounds and various generations. Then we will move it on persistent current, the current which exists in a solenoid that is superconducting and no external source is needed for this persistence. Already we have many applications developed and Japanese are using maglev trains based on this. So this is given in this syllabus. The objective and learning is about development of such interesting phenomena of zero resistance, current at zero resistance and application of persistent current, the current that can exist even more than 1 lakh years or million years. So we will talk about this in this lecture. This lecture will give you a lot on understanding the things, why superconductors are more important and why still we are searching for high-T superconductors. Such type of chapters and issues can help us in development of energy saving devices. If the current can exist for a long time without any resistance, then many transformers, superconducting transformers can be developed. Many things where energy loss will be zero. Superconductors gave us a hope that soon we can develop such type of applications. But to move there, we have to learn many theoretical aspects of this. We must have some critical and innovative skills to think and ask about applications about this. Superconductivity. The word first came into picture in 1911. Something that discussed by Kamerlingh Onnes. In 1911, he proposed a theory based on their experiments. He said that the electrical resistivity of many metals and alloys drops suddenly to zero when it is cooled to a sufficiently low temperature. And he got the temperature about a liquid helium range. The event was very surprising to him. Why the resistance suddenly reduced to zero? Term this as superconductors. Superconductors which are having zero resistance. I think we must revive these things here. Materials can be divided into two categories. One are conductors like metals, copper, where electron can flow freely from them, and one are insulators. Electron can't flow. With this, the physicists also developed a lab to cool materials to temperature near absolute zero, means minus 273 degrees Celsius. They tried to invest what the ability to conduct electricity at these lower conditions. In some simple elements such as mercury and lead, they noticed something remarkable below a certain temperature. These materials could conduct electricity with no resistance. This behavior is very different. And this is known as superconductors, the exotic third category that conduct electricity perfectly. And if you send the current through these wires, the current never degrading or dissipating. That is very interesting. We started this topic in the last chapter, and we will further develop the idea of persistent current here. The temperature at which the specimen suddenly give new behavior, that is called critical temperature. The temperature at which a transition takes place. A state of normal electrical resistivity to superconducting state. That is called critical temperature, TC. We do know that. Superconductivity is now very well understood. It has many practical and theoretical aspects. Here in this lecture, we are discussing some experimental aspects of superconductors. Superconductivity is a phenomena occurring in certain materials at low temperature. this which is characterized by the complete absence of electrical resistance and the damping of the interior magnetic field, which we will discuss later. We can give a background about this, then which materials give superconductors, so behavior and everything that is worked out to increase the temperature of superconductive behavior, increase the temperature of TC, because this is possible only at or below TC. That is the reason we are interested in study the behavior of occurrence of superconductivity. Superconductivity occurs in many metallic elements of periodic table and also in alloys. It is also there in intermetallic compounds and doped semiconductors. We begin our search with metallic elements. Then many alloys have been developed based on cuprate alloys and other types of alloys. Then some doped super semiconductors also there. Everything is about to increase the temperature. As we try to understand the behavior, we search new materials. The range of transition temperature best confirmed at present, it is about YBCO at 90 K. However, many new materials also been invented for higher TC. For some transition materials, the transition temperature is 0.001 K. Several F-band superconductors, these are also called exotic superconductors. Several materials become superconducting only under high pressure, and this started the thirst of researching high pressure superconductors. Silicon has a superconducting form at 165 kilobar with 8.3 K. We have discussed several superconducting elements for zero pressure in the next slide. We have this query: will every non-magnetic metallic elements become a superconductor at sufficiently low temperature? Exactly, we don't know the answer. However, we are working on this. In experimental researches for superconductors at ultra low transition temperature, that is true that it is important to eliminate specimen even trace quantities of foreign paramagnetic elements. If you have paramagnetic elements in the compound, in the specimen, then they can severely reduce the transition temperature, and we are always interested to increase the transition temperature. So that is interesting. We have only one part of iron in 104, then this will destroy the superconductivity of molybdenum, which then pure has ETC 0.92 K at 1 atmospheric pressure percent of gallium, then this lower the transition temperature from 5.6 to 0.6 K. So this is very important. The presence of magnetic behavior, magnetic compound may reduce the temperature. However, non-magnetic impurities have no marked effect on transition temperature. That can be there. So these are a few conclusions that we have drawn based on experiments. Element that can give superconductivity shown here, and the length in the 3D figure is showing you higher Tc. Calcium having high Tc, then lithium also there, and whereas we have shown those elements which are having greater than 25 K with red, then 20-25 with yellow, 15 to 20 with green, and so on. Dark blue is less than 1 K. So these are the material that gives the superconducting behavior. Elements have limited possibilities to increase the transition temperature. So we move to compounds. These are few compounds gives superconducting behavior. However, after this, many new compounds have been searched, and it is still a matter of research how to increase the Tc transition temperature. Now, several organic compounds also show superconductivity at lower temperatures. So, a lot of work is still to be done for increasing Tc. Although many applications we have developed, but it is needed to increase the Tc for enhancing the application part of this. One of the interesting factors about the superconductors are persistent current. As we know, the perpetual electric current not requiring an external power source, that is called persistent current. The current which is without power source. Such type of arrangement can be made with superconductors. As we know that in electromagnetism, then all magnetization can be seen as microscopic persistent current. The current can be replaced by magnetization, and such arrangement can also be done with superconductors. If we apply a magnetic field perpendicular to the plane of ring, the temperature we keep at above the critical temperature of the material which is from which the ring is made, then the magnetic flux phi through the ring will be V0A. And now if we cool the ring below critical temperature, then the flux passing through that will not change. And so the flux will be trapped there, which is responsible for persistent current that we are talking. As we have seen here, the circuit has no resistance below DC. And since circuit has no resistance, the current can flow indefinitely. And the original amount of flux can be maintained indefinitely. So this is very good application of the superconductors persistent current. The current can be developed and which is almost all the time till the material is in superconducting range below DC. Without any external source, we can obtain current. Whatever we have discussed, this is shown here in the figure. We have kept one ring in magnetic field and then we kept it at lower temperature, and at lower temperature we stop the magnetic field. Now the magnetic field flux is trapped here, and this magnetic flux gives us current. In superconducting state, the DC electrical activity is zero. So close to zero, the persistent electrical current have been observed to flow without attenuation in superconducting rings for more than a year, until, since we have this experiment here. That persistent current, or you can also say at supercurrent, may be decayed, and at what time it will take was studied by Filey and Mills using piston nuclear magnetic resonance method to measure magnetic field associated with the supercurrent. And they concluded that the decay time of a supercurrent is not less than 1 lakh years. So you can assume that if a supercurrent is there, a long time is needed to decay. In some superconducting material, particularly those used for superconducting magnets, finite decay time are observed because of an irreversible redistribution of magnetic flux in material. But whatever it is very exciting. You can get the current without any external source for a long time, and it has many applications can be developed, or still already been developed. Superconducting coil with persistent current can be used in high-speed magnetically leviated trains. It is already being used in Japan in Yamanashi maglev test line as shown in the figure. The superconducting coils mounted on side of the train induced current in coil mounted on the wall of a guideway. Here it is shown here. And repulsive force between the superconducting magnets and the track mounted on the coil. Both leviate the train and provide lateral guidance. The train is propelled forward by attractive and repulsive forces between superconducting magnets and propulsion coil located on the wall of the guideway. This train in 2003 reached a record-breaking speed of 581 km per hour on the street. So this is one of the most important application of superconducting persistent current. I'm giving you two exercise here. Write a short note about life of the universe and persistent current in superconducting coil. Can you compare this? If a coil continues for a long time, if you can manage this, then can you compare these two? Another question I'm also giving you. Can you comment on this? Then compound superconductors are much better than elemental superconductors. In what way? I'm saying. And if those are better, what are the stages that we have developed? Or how many types of superconductors we have developed? Work on. I've used following two references: Introduction to Solid State Physics by C. Kittle, Charles Kittle, while of publication, and this openware, OpenLearn for application purpose of superconductors. It is always useful to go through the websites and learn so many things about superconductors. Thank you. We have learned about persistent current. In the next lecture, we will talk about Meissner effect, how this take place in superconductors and the applications of this Meissner effect. Thank you.